All right, everybody. Dan is gonna continue with his third lecture.
Well, thank you very much. So let us carry on. Let us say a few words about cohomology. So once again, let X be say a compact complex manifold. A compact complex manifold of complex dimension n. And remember that we have the differential operator D acting on differential forms that splits into two parts, del and del bar. So actually the complex structure can be seen as this splitting, right? So the complex structure is this splitting. Complex structure of X. So del is the 1-0 part. It takes functions to 1-0 forms and d by the 0-1 part. And now we have d squared equals 0. And this implies that del squared equals 0 because this is the 2-0 part of d squared. Del is type 1-0, so the square is type 2-0. Del bar plus del bar del equals 0. So this is the 1-1 part of d squared. And d bar squared equals 0. It's the 0-2 part of d squared. Now, d depends only on the differentiable structure. D depends on the smooth structure, on the C infinity structure of the manifold. And because d squared equals 0, it induces a cohomology that is called the de Rham cohomology. So this is the first cohomology that we're going to see today. So the de Rham cohomology. Oh, sorry. The de Rham cohomology of X. So because d squared equals 0, we get a complex, right? We have a complex. Now, what is a complex? It is a sequence of vector spaces with maps. So let's look at the C infinity forms of degree k on XC. So this is the space, the vector space of smooth k forms. Smooth k forms on X. So if we apply the operator D to them, we differentiate them once, so we get k plus 1 forms. So C infinity k plus 1. And of course, we can continue by applying D and so on. And the previous space in the sequence is the space of k minus 1 form. So C infinity k minus 1. And so on. And the complex means that the image of any map is contained in the kernel of the next one, which is equivalent to saying that d squared equals 0. So this is exactly what we have, because d squared equals 0. So the image of d, we're acting in k minus 1, in degree k minus 1, is contained in the kernel of the next d. But in general, we need not have equality, right? We need not have equality. And the cohomology measures how far we are from having equality, right? So this is a complex. Complex means exactly what I said, that the image of each map is contained in the kernel of the next one. And then we define, so definition, for every k, in theory for every k in Z, but it only, we get non-trivial things only if k is between 0 and the real dimension of the manifold. So 0, 1 up to 2n. This is the real dimension of X. The complex dimension is denoted by n. So for every k, we set hk de Rham, dr stands for de Rham of xc. So this one is the vector space that measures how far, by how much, this inclusion fails to be an equality. So we take the kernel of d acting in degree k, so d acting on k forms, on C infinity k, with values in k+1 forms, le quotient are by the image of the previous D. So the kernel of the outgoing D, if we fix the degree K, quotiented out by the image of the incoming D. So the image of a D acting on k-1 forms and landing in K forms. So this is called the Durham cohomology group. Actually, it's even a vector space. In particular, it's a group. The Durham cohomology group of degree K of the manifold. Durham cohomology group of degree K of X. So it is a C vector space. It is even a C vector space. And the miraculous thing, I don't think I'll have time to prove this, but it's a fundamental fact. So let me just state it. Maybe I can say a few words about the proof, but the proof would need time to do it. Fundamental fact is that when X is compact, and we did assume this, I think, we supposed it to be compact, but let me repeat it. When X is compact, because otherwise what I'm going to say is not true. If X is compact, the Durham cohomology space has finite dimension. So the dimension is a C vector space, the dimension of a C of HK Durham of XC is finite. Right? This means finite. So one way of proving this is using PD theory, what is called the elliptic theory. So let me just say briefly. So idea of proof. We can consider what is called the D Laplacian. Consider the D Laplacian. Defining the following delta, it is denoted by delta. We take d star plus d star d, where d star is the adjoint of d, where d star is the adjoint of d with respect to a metric. But I haven't said yet what a metric is. So maybe I'm getting a bit ahead of myself. With respect to a Hermitian metric, so I'll say this in a few minutes time, with to a Hermitian metric, omega on X. So if you bear with me for a few minutes, you'll see what this is. So this is an operator acting on differential forms, on C infinity differential forms of any degree. So here, let's take K forms with values in themselves. And the crucial fact is that this is an elliptic operator. It's an elliptic differential operator. Elliptic and self-adjoint. Elliptic, self-adjoint, and a non-negative differential operator. And it is a fundamental fact of life, a PD fact, so fundamental PD theory or harmonic theory fact is that for any elliptic operator on a compact manifold, and this is the case we have here, the kernel is finite dimension. So the dimension of the kernel of delta is finite, right? Finite. And the image is closed. And on the other hand, so another fact is what we call the Hodge isomorphism. So these things, I'm only stating them, so I don't have time to prove them. I will need much more time for this. The Hodge isomorphism states that the cohomology space HK Durham that we defined is actually isomorphic to the kernel of this Laplacian, to the kernel of a delta acting on C infinity K forms with values in C infinity K forms. So this kernel is called the harmonic space or delta harmonic space. This one is called the delta harmonic space. And these are the rudiments of Hodge theory. So the cohomology space is of algebraic nature, right? This is an algebraic object. You can define this purely as, you can regard this purely as an object in homological algebra. You just take a complex, the Durham complex. Of course, it's not entirely algebraic because in the Durham complex, the operator D is a differential operator, right? So, but you can regard it as a purely formal object. You take a complex, for example, Durham complex in this case, and define its cohomology, whereas the harmonic space is an analytic object, right? So the Hodge isomorphism is an isomorphism between an algebraic object and an analytic object, and the idea is actually to do analysis by studying this elliptic operator, and then to recover information that has an algebraic and also a geometric meaning. So this is the beginning of Hodge theory. And now, as for the terminology, so since X is compact, and since these spaces have finite dimension, their dimensions are very important. They are in topological invariants that are called the Betti numbers. So for every K, we set B sub K, so this is called the kth Betti number, the kth Betti number of the manifold. This, by definition, is the dimension over C of HK Durham, of the cohomology group of degree K. So the Betti numbers of a compact manifold give topological invariants. So these are topological invariants. So the invariants, they're invariants because, for example, they don't change if you take a manifold that's diffeomorphic to the original one. They depend only on the differentiable structure of the manifold. So these are topological invariants. These are topological invariants of the manifold. And let me give you an example. In degree 1, so when K equals 1, H1 Durham of the manifold. So as groups, they are abelian, of course, right? Because they're even vector spaces. And the underlying group of a vector space, of course, abelian. But H1 Durham is the abelianization of the fundamental group of the manifold. This one is the abelianization of the fundamental group pi1 of X. So in particular, if X is simply connected, the fundamental group is trivial and the abelianization is also trivial. So for every simply connected manifold, the first Betti number is 0. So in particular, so intuitively, simply connected means that there are no holes. In particular, if X is simply connected, so if it has no holes, its first Betti number, B1 of X, vanishes. Right? And now we can do, so this is the drum cohomology. From our point of view, its main feature is that depends only on the differentiable structure of the manifold. So let me see, did I put a number here? Yeah, I put number 1. And now let's do the same thing, number 2, but for d bar, right? Now, d bar squared is also 0, hence we get what is called the Dolbeau cohomology. Dolbeau cohomology of the complex manifold of X. And unlike the de Rham cohomology, this one depends on the complex structure.
May I ask something?
Yeah, please.
It's you said that it's differentiable invariant, but if you have different differentiable structures, don't you get the same de Rham cohomology?
No.
No?
It depends on the differentiable structure, the de Rham cohomology.
Oh, really?
Yeah.
Oh.
But in our case, since we're doing complex geometry, you usually fix the differentiable structure and only vary the complex structure.
I mean,
So
the
this is,
dimensions doesn't change, but the product changes probably if you change the differentiable structure. Is it what's happening? Yeah.
well, actually, no, it's even a topological invariant. So it depends only on the topological type of the manifold.
Yeah, right.
Because there's a whole theory here. Of course, this is the de Rham cohomology, but you can also define the homology, and that
Yeah.
one, and they're isomorphic, and that one depends only on the topological structure of the manifold.
Right.
But from
I see.
our
So,
point of view, we're fixing the differentiable structure, and we're varying only the complex structure.
all right. So if you for example have a manifold without differentiable structure, then
You can still define the homology in a
Mhm.
topological way. And if you have a differentiable structure, the homology is isomorphic to the cohomology, to the de Rham cohomology.
Okay.
So these are actually topological invariants. It's
Topological.
much more than differentiable invariants, and even topological invariants, right? But
All
since
right.
here we are
Homotopy.
concentrating on the smooth structure and the
Maybe
complex structure,
not homotopy theoretic, right? So
right?
only. Okay. Thank you.
Now the Dolbeau cohomology of X, this one depends on the complex structure. Unlike the de Rham cohomology, which doesn't. So we start off with a complex. It's defined in a way analogous to the de Rham cohomology. Right? So we have the Dolbeau complex. So it is a complex because d bar squared equals 0, but we have to take by degrees here. So we look at PQ forms that are C infinity, smooth. And then we have an outgoing d bar and an incoming d bar. So the outgoing d bar takes us to PQ plus 1 forms. So the d bar increases the anti-holomorphic degree by 1, and the incoming d bar comes from PQ minus 1 forms. And because d bar squared equals 0, so this is the main thing, the image of the incoming d bar, so the one coming from PQ minus 1 and getting into PQ, is contained in the kernel of the next one. The image of d bar acting on PQ forms with values in PQ plus 1 forms. And as usual, because this is a complex, we define the cohomology as the quotient of these of the larger space by the smaller space. So the cohomology measures how far we are from having equality. So we define for every P and Q. So again, in theory, they can be any integers, but we get non-trivial things only if P and Q are from 0 to n. We put HPQ d bar of XC. So by definition, this one is the kernel of d bar acting in by degree PQ with values in PQ plus 1 forms, quotiented out by the image of the previous d bar, the one coming from PQ minus 1 forms and landing in PQ forms. So this one is called the Dolbeault cohomology group of bi-degree PQ. Dolbeault cohomology group, but it's a vector space as the Durham ones. The Dolbeault cohomology group of bi-degree PQ. Right, and now the fundamental question is the following. So, well, trivial observation. At the level of the forms, so we always have, for every k, at the level of the forms, we always have a decomposition. Every k form splits uniquely, and therefore the space of smooth k form splits as the direct sum over p plus q equals k of the smooth PQ forms whose sum p plus q equals k, right? Because any form splits uniquely alpha as a unique decomposition into pure type form, right? Alpha p0 plus alpha p minus 1, 1, and so on, up to alpha. It's not p0, so it's k0, sorry. Right, alpha k0, if alpha is a k form, alpha k minus 1, 1, and so on, up to alpha 0k. So at the level of the forms, we always have a decomposition, right? At the level of forms. And this decomposition depends on the complex structures. This is what the complex structure does, right? Because the bi-degree is actually induced by the complex structure. But the fundamental question is, do we have fundamental question? Do we have a similar decomposition at the level of the cohomology? Do we have the same thing in cohomology? In other words, is it true that HK Durham of XC splits equals, or well, canonically isomorphic, because not necessarily equal. Is it canonically isomorphic? To the direct sum of a p plus q equals k of HPQ Dolbeault. And do we have this for every k? For every k from 0, 1 up to the real dimension 2n of the manifold, right? So this is the fundamental question that we start off with. And why is it important to answer this question? Because this would be a way to link the differentiable structure of the manifold. So once again, the Durham cohomology group depends only on the differentiable structure, right? The smooth structure, the C-infinity structure of X. Whereas the Dolbeault cohomology groups depend on the complex structure. So this would be a very efficient way of linking these two types of structures on the same X. The complex structure of X. So once again, we have the similar thing at the level of forms, but at the level of forms, it's not satisfactory. Of course, it's nice to have it at the level of forms, but it's not entirely satisfactory because these vector spaces at the level of forms are infinite dimension. So these are infinite dimension vector spaces. So we don't get topological information on the manifold directly from the decomposition at the level of forms. But at the level of the cohomology, these spaces are finite dimensional. So we'd get important topological information from this thing if it happened. So let's call this star. Now, let me just give the answer first, and then I explain what happens. In general, the answer is no, unfortunately. So answer, in general, no. However, it is yes in some important special cases. However, it is yes if X has an important property. It's not if and only if. It only goes one way. If X has a certain property, then the answer is yes. Right? And now let me give this definition. So what I'm going to say now is well known, but people don't usually present it in the way I'm going to do. And I'll tell you later what is the difference with respect to the standard case. So let me give a definition now. Let us introduce a notion that I like to call DD bar manifold. So let X be a compact complex manifold. Let us fix n its complex dimension. So we say that X is a DD bar manifold. So this is the notion we're defining now. If and only if, by definition, the following thing happens. For every k from 0, 1 up to the real dimension 2n, or let's say rather for every p and q, so in any bi-degree, I mean, for every bi-degree pq, so for every p and q from 0, 1 up to the complex dimension n, and for every alpha C infinity PQ form on X, the following conditions are equivalent. The following equivalences hold. Alpha, and if alpha is declosed, right, for every alpha such that d of alpha equals 0, once again, we say that the manifold is a DD bar manifold if for every pure type form, alpha, that is declosed, the following equivalences hold. Alpha is D exact, in other words, alpha is in the image of D, if and only if alpha is del exact, that is in the image of del, if and only if alpha is D bar exact, that is in the image of D bar, if and only if alpha is DD bar exact, in the image of DD bar. Right? So this is the definition. There isn't much to look at because it looks a bit abstract, but it's very powerful. So you can look at it as a kind of symmetry of the complex structure, right? The manifold is a complex manifold, therefore it has a complex structure, which is defined by the splitting of D into del and del bar. And this is a kind of symmetry of the complex structure, right? We require that all the exactness properties with respect to D, with del, with respect to del bar, with respect to del bar to be equivalent for any pure type declosed form alpha, right? So it's a kind of symmetry. It is a symmetry property for the complex structure. Right, and not all manifolds satisfy this. I'm going to give you some examples. But now let me state a theorem. If X is a DD bar manifold, then what I said before, this canonical isomorphism between the de Rham cohomology and the Dolbeault cohomology holds. And when this canonical isomorphism holds in a certain ways, I'm going to describe it, we say that we have a Hodge decomposition on the manifold. And actually it's equivalent to the manifold being DD bar. Let's just state the theorem one way, but it actually goes both ways. So let X be a compact complex manifold. Let us assume that is DD bar. let X be a compact DD bar manifold of complex dimension n. And then two things happen, or maybe three things. Let's say the following thing. For every k, and for every Durham cohomology class of degree k, or let's say, let's put it differently. In every bidegree PQ, for every P and Q, and for every Dolbeault cohomology class of bidegree PQ, so for every alpha that lives in HPQ D bar, Dolbeault cohomology class. So remember, Dolbeault cohomology classes are representable by PQ forms that are D bar closed, right? Because that are in the kernel of D bar by definition. Because we define the Dolbeault cohomology by taking the kernel of D bar and quotienting it out by the image of D bar. So a PQ form that's only D bar closed has no reason to be D closed. But what we says is that under the DD bar assumption, every Dolbeault cohomology class can be represented by a D closed form. So for every Dolbeault cohomology class, there exists an alpha twiddle, so in the same Dolbeault cohomology class, such that alpha twiddle is closed, is D closed. So under the DD bar assumption, every Dolbeault cohomology class can be represented by D closed forms. Now, second, for every k, the following map, the following linear map. So I'm taking the following thing. The sum of a P plus Q equals K of the Dolbeault cohomology, HPQ D bar of XC. And I want to map this to HK Durham of XC. Now, what am I going to do? I need to, in each Dolbeault cohomology class, I know by the first assertion that there exists a representative that's D closed. I choose any alpha PQ such that it is D closed, D of alpha PQ equals 0. So I represent any Dolbeault cohomology class by such an alpha PQ. And now an element in the direct sum is the family of such classes. That is one such class for everybody PQ, such that P plus Q equals K. And I map this element in the direct sum to what? So first of all, I'm taking the sum of the representatives of a P plus Q equals K. Now, this is D closed because each representative is D closed, right? And I know that I can find a D-closed representative in each class by the first statement. And then I'm taking the Durham class of this sum. And now the statement is that this map is, on the one hand, well-defined. Well-defined means that it does not depend on the choice of D-closed representatives, right? Because the first point says that every Dolbeault class can be represented by D-closed form, but that D-closed representative is not unique, right? So this map is well-defined. And this means that it is independent of the choices of D-closed representatives. But they have to be D-closed, independent of the choice of D-closed representatives alpha PQ of the Dolbeault classes. Right? It is well defined, and moreover, it is an isomorphism. And is an isomorphism of vector spaces. So you see, this map, of course, is canonical because it's almost the identity. You take any, you represent once you've represented the Dolbeault classes by declosed forms, the map is actually the identity. You just move the alpha PQs on the left, you move them on the right, take their sum. So the map induced by the identity, of course, if it's well defined in an isomorphism, and this is what this theorem states under the DD-bar assumption on the manifold, then it is canonical. It is induced by the identity, right? And now, let me say here, if this property of X, so once again, which property? The property that the Dolbeault homology is isomorphic, canonically isomorphic to the de Rham homology via the identity map, the map induced by the identity in cohomology, is called the Hodge decomposition. It's called the Hodge decomposition property of X. The Hodge decomposition property of X. But not every manifold has it. Only DD-bar manifolds have it. So the converse is also true. So if X is a DD-bar manifold, then we have this. And now, third thing, under the same DD-bar assumption, there is another property called Hodge symmetry. So it states the following thing. For every P and Q, from 0 to the complex dimension n, the map, the following map. So I'm looking at the Dolbeault homology group HPQ D-bar, and I'm going to map it to HQP D-bar. But then I have to take the D-bar here because I want to get a linear map. So let me explain. So how is this map defined? In general, there is no such map. Because if we take a class here, alpha P, represent a Dolbeault class represented by an alpha PQ, in general, alpha PQ is only D-bar closed. So we'd like to map it to the class of its conjugate, alpha PQ bar. So in general, this is not well defined because in general, an arbitrary representative is only D-bar closed. And this is equivalent to saying that its conjugate, that is del of alpha PQ bar, is 0. But in general, alpha PQ bar has no reason to be D-bar closed. It's only del closed. So in general, alpha PQ bar is not D-bar closed. However, here we have shown, we haven't shown it yet, but we have stated that under the DD-bar assumption on the manifold, every Dolbeault class can be represented by a D-closed representative. So we choose alpha PQ to be D-closed. We choose alpha PQ such that it is D-closed. So we know that this thing is possible by the first assertion. And then if it is D-closed, this means, because it's a pure type, that it is both del and D-bar closed. Right? But now if I choose the first property here, the one saying that it's del closed, right? If I take this away, this is equivalent, so it implies by conjugation that D-bar of alpha PQ bar is 0. So alpha PQ bar now defines a Dolbeault homology class, right? And the statement is that this map, so I started stating it here, and then let's isolate this map here. Defined using D-closed representative. So the map, let's call it star. So the statement is that the map star defined using D-closed representatives alpha PQ, using alpha PQs in the kernel of D, is well defined So again, well-defined means that it is independent of the choice of representatives. because a declosed representative exists by the first statement, but it need not be unique. So if you choose another declosed representative of the same class, you get the same class here. So it is well defined in the sense that it is independent of the choice of representatives, and it is an isomorphism. It is well defined and an isomorphism. Now, this property of the manifold, which doesn't hold in general, but holds under the DD-bar assumption, is called the Hodge symmetry, right? Because there is a symmetry between PQ and QP. So, this isomorphism is canonical. Again, it is induced by the identity. Yes? You take the same representative on the left and right, you just do the obvious operations to it, you conjugate it, the conjugate of the identity. So this property of X is called the Hodge symmetry property. Hodge symmetry property. And actually have more. So what I stated here is that if X is a DD-bar manifold, then we have Hodge decomposition and Hodge symmetry. Actually, the converse is also true. Having Hodge decomposition is equivalent to the manifold being DD-bar. Now, let me give you just an idea. I'm not going to prove everything because it take too long, but I can prove something. Actually, if you have proved one of these things, if you have understood how one of these things is proved, you can prove the others in a similar way. So let me prove the first part, part one, and then the others are proved in the same way. Proof of one. So what does one say? It says that if you every Dolbeault class can be represented by a declosed form. So let us give ourselves a Dolbeault class. But giving a Dolbeault class, let us give any representative of it. So let alpha be a PQ form, C infinity PQ, such that, so a priori, it is only D-bar closed, right? Because it represents a Dolbeault class. So D bar alpha equals 0. So representing the Dolbeault class. Dolbeault cohomology class, alpha sub D bar. And we want to show that alpha can be modified, but without changing the cohomology class, to something that's declosed. So we want to show that there exists an alpha twiddle, but be careful. So alpha twiddle needs to be modified from alpha in such a way that we don't change the Dolbeault class. But since the Dolbeault cohomology is defined by cautioning out by the image of DD bar, if we don't want to change the class, we can only add DD bar of something to it. Right? So we want an alpha twiddle of the same bi-degree PQ. So actually we want a beta, right? Beta will be of type P minus 1, Q minus 1, if we want its DD bar to be PQ. So we want an alpha twiddle to exist. In other words, we want a beta to exist such that, sorry, what am I saying here? We're in the Dolbeault cohomology, so it goes by D bar, sorry. So beta will be of type PQ minus 1. Right? The Dolbeault cohomology is quotient of D bar, kernel of D bar, quotiented out by the image of D bar. Right, so if we don't want to change the cohomology class, we can only add D bar of something, so D bar of some beta. So this one will live in the same Dolbeault cohomology class of alpha. So we want to be able to find an alpha twiddle, in other words, a beta, such that D alpha twiddle is 0. But D alpha twiddle being 0, since alpha twiddle is of type PQ, is equivalent to del alpha twiddle being 0 and D bar alpha twiddle being 0. Now, the D bar alpha twiddle being 0 is automatic. This is automatic because alpha has this property, right? D bar alpha is 0. Alpha is the original thing, right? Which represents our Dolbeault class. It is 0. And D bar beta is also in the image of D, in the kernel of D bar. So D bar beta that we have here is also in the kernel of D bar because D bar squared is 0. Right, the first property is automatic. So we only need to ensure the second property, right? So let's see what this means. We want del alpha twiddle to be 0, but this is equivalent to what? Alpha twiddle is going to be alpha plus d bar of some beta. We're looking for beta, right? So del alpha twiddle is del alpha plus del bar beta. So we want this to be 0. So in alpha is given, we're looking for beta. So what does this mean for beta? It means that beta has to satisfy the equation dd bar beta equals minus del alpha. And this equation is solvable. In other words, we can find such a beta if and only if the right-hand side term, which is minus del alpha, is dd bar exact, right? In the image of dd bar, right? So this equation is solvable. In other words, such a beta exists if and only if the right-hand side term, del alpha or minus del alpha is the same thing, is in the image of dd bar. It is dd bar of something. And this is where we're going to use the dd bar assumption, right? Now, let us remember that del alpha is a pure type form because alpha is of type PQ. So del alpha is of type P plus 1Q, is a P plus 1Q form. And let's see, is it declosed? D of del alpha is what? Is del of del alpha, so that's del squared del alpha, plus d bar of del alpha, that's d bar del alpha. Now del squared is 0. And d bar del anti-commute, remember that del bar plus d bar del is 0, because that's the one part of d squared. So del and del bar anti-commute, so that's minus del of d bar alpha, but d bar alpha is 0 by hypothesis. Remember that alpha was any representative of our Dolbeau class, and as such, it is d bar closed. Right? So d bar alpha is 0, and therefore its del is also 0. So our del alpha is a PQ form. In other words, P plus 1Q form. In other words, it has pure type. It is declosed because d of it is 0, as we just saw. And on the other hand, del alpha is obviously in the image of del by construction, right? Because it is del of something. In other words, we can apply the dd bar assumption to it, right? It's a pure type form that's declosed and it is del exact. But since the manifold is a dd bar manifold, all the exactness properties are equivalent. So anything that's del exact, in particular del alpha, is also dd bar exact. And this is it. Now, since X is a dd bar manifold, del alpha is also exact in all the other senses. In particular, it is dd bar exact. And we're done, right? It is dd bar exact, and therefore we can find a beta as we want. A beta such that dd bar beta is this, a QED. Right? And the other statements of the theorem can be proved in the same way, right? So if the manifold is a dd bar manifold, then it has the Hodge decomposition property and also the Hodge symmetry property. And actually, Hodge decomposition implies Hodge symmetry. And Hodge decomposition is equivalent to the manifold being dd bar. Right. Now, before moving on to metrics, let me introduce two other types of cohomology. Let us call them Botchern and Epley cohomologies. Now, in the Botchern case, we define HPQ Botchern, so BC. By definition, it is the kernel of del intersect kernel of del bar, quotiented out by the image of del bar. So this is the finest cohomology because the finest cohomology, because we require the representatives to be both del and del bar closed. So this is the strongest notion of closedness that I have. And we also quotient out by things that are in the image of dd bar. This is the strongest notion of exactness that we have. So it's very restrictive. It's very precise. And at the opposite end of the spectrum, the Eppler cohomology is the coarsest one, HPQA. So here we're taking forms that are only in the kind of del bar. So this is the coarsest notion of being closed, and we quotient out by forms that are in the image of del plus image of del bar. So this is the coarsest cohomology that we have. And an immediate observation is that the Bochern cohomology maps canonically into all the other cohomologies, whereas all the other cohomologies map canonically into the Eppler cohomology. So let me write this. The following canonical. Canonical means that they only depend on the complex structure of the manifold. They don't depend on any other thing like metrics. Following canonical linear maps. Now I'm going to see that they're well defined. So again, they're induced by the identity. So let's see, from Bochern, HPQ Bochern, to HPQ Dolbeau, so HPQ D bar, to HPQ Eppler. So all these maps, I'm going to define them, are well defined. So they're induced by the identity. In other words, we're giving ourselves any Bochern class with any representative alpha. And the map is defined by mapping this to the Dolbeau cohomology class of the same representative. And if you want to go from Dolbeau to Eppler, do the same thing. We take the map induced in cohomology by the identity. We map the Dolbeau class of alpha to the Dolbeau class to the Eppler class of alpha. So these linear maps are well defined. Well defined. So well defined means that, for example, they don't depend on the choice of representatives. And same goes for the map from Dolbeau, from HPQ Dolbeau to Durham. So here we're going to take HP plus Q Durham of XC. Again, we're taking the map induced by the identity, Dolbeau class of the Bochern class of any alpha is mapped to the Durham class of the same alpha. And the other way around, from Durham to Eppler. But let's stop here. So proof. Well, let's check one of these. For example, let's look at Bochern to Dolbeau. So we have to check two things in order to check that the map is well defined. So if alpha represents a Bochern class, then del alpha equals 0, and d bar alpha equals 0. Right, because the Bochern cohomology is defined in this way. It is representatives are both del closed and d bar closed, right? So if we have this alpha representing a Bochern class alpha BC, then in particular it represents a Dolbeau class, right? Because it is d bar closed. So let's take away only the second property here. This implies that alpha represents a Dolbeau class alpha d bar. So that's one thing we needed to check in order to check that this map here, let's call it TPQ, is well defined, right? That any representative we take on the left produces a class on the right. But this is not enough. We also have to check that this is independent of the choice of representatives, right? Now let us check that the map TPQ is independent of the choice of a representative. So what does this mean? It means that if we represent the same Boolean class by another form alpha twiddle, the Dolbeau class of alpha twiddle coincides with the Dolbeau class of the previous representative alpha. So let us take alpha and alpha twiddle C infinity PQ forms, such that they represent the same Boolean class. So we have to assume that they're both del and d bar closed. And crucially, they represent the same Boolean class. In other words, there exists a beta such that alpha twiddle equals alpha plus dd bar beta. So this condition means that alpha and alpha twiddle represent the same Boolean class. And now in order to show that our map, so let's go back to the map. In order to show that our map TPQ is well defined, we need to show that on arrival, they represent the same Dolbeau class. The same Dolbeau class. So if they represent the same Boolean class on departure, they must represent the same class on arrival. Because otherwise, the map would depend on the choice of representative, so it wouldn't be well defined. So we need to check that Boolean class, Dolbeau, of alpha twiddle is the same as the Dolbeau class of alpha. In other words, this is equivalent to checking that the difference alpha twiddle minus alpha represents the zero Dolbeau class. In other words, it is in the image of d bar. This is what we want to check. Let's put a question mark. But now this is clear because we assumed more actually. We assume that they represent the same Boolean class. That is, we assume this. And from this, we want to deduce that they represent the same Dolbeau class. We have alpha twiddle minus alpha. It is del bar of beta. But del and del bar anti-commute. That's minus d bar of del beta. So it's d bar of minus del beta. So this belongs indeed to the image of d bar. Right? It's d bar of something. And this is what we wanted, right? We wanted exactly this. The difference is d bar exact, and it is, because it's even d bar exact. Right, so QED. Right, so this is the proof of the fact that every Dolbeau class can be represented. This is the proof of the fact that the map from Boolean to Dolbeau, based on TPQ, is well defined. And the other things are proved in the same way. Once again, let me stress something. This immediate observation holds with no assumption on the manifold. Don't have to assume that the manifold is d bar. This one requires no assumption on X. So the Boolean cohomology maps canonically into all the other cohomologies. We proved that it maps canonically into Dolbeau, but also into Epley, and also into Durham. And all the other cohomologies map canonically into Epley. There's no assumption to be made on X to have this. This always holds. But now another thing that I'm going only to state, it can be proved in a similar way as we proved the previous theorem. By the way, these maps that are canonical here, that we wrote, these maps need not be either injective or surjective. They're just well defined. But in the DD bar case, they're isomorphisms. So this is the theorem. If X is a DD bar manifold, all the above canonical maps, all the above canonical maps are isomorphisms. In other words, on DD bar manifolds, these cohomologies that we defined are all canonically isomorphic. Right? And now, well, I'm going a bit fast now because, so what we've seen so far is just the cohomological point of view of things. Now let's look at a different point of view now, too. And this is actually the theme of this course. The metric point of view. The metric point of view. In other words, we want to know whether the existence of a certain metric on the manifold produces the properties that we saw in the D-bar case above. So the question is, does there exist any class of metrics on X such that guaranteeing that X is a DD bar manifold? So does there exist a class of metrics on X implying that X is a DD bar manifold? So again, we'd like to link two kinds of notions. The property of being a DD bar manifold is a cohomological property. So it's essentially algebraic or topological, if you wish. And metrics that I'm going to define now are analytic objects or differential geometric objects. We'd like to know whether a differential geometric object implies a topological property. In other words, whether the existence of a certain kinds of metrics implies the DD bar property. Now, let's start with the definition. So let X be a compact complex manifold. It doesn't have to be a compact. Let X be a complex manifold. Let us denote by n its complex dimension. And now, what is a Hermitian metric? A Hermitian metric on X is the following data. So we require that for every X, every point in the manifold, we require that we have, there exists an inner product. An inner product, depending on X, on the fiber, on the tangent space to the manifold at X. In other words, on the fiber at X of the tangent bundle, of the holomorphic tangent bundle, on the holomorphic tangent space, the one that we denoted by T10, tangent space to capital X at lowercase x. So an inner product on the holomorphic tangent space right? And second, we require these inner products to depend in a smooth way of the point, and such as the map, taking the point lowercase x in capital X to the corresponding inner product is a C infinity map. Right, so a Hermitian metric on the manifold is to give a Hermitian metric on the manifold means to give an inner product on each tangent space, holomorphic tangent space, in such a way that these inner products depend in a C infinity way with a point. Now, in local coordinates, so this is the definition. Now, in local coordinates, the metric is given as the metric, let's give it a name. The metric G, say, a Hermitian metric G. The metric G looks like the following. So G is the sum of a j and k from 1 to n. There are coefficients here. G, j, k bar times dzj tensor dz bar k. So what's the meaning of this? This is just actually a notation for what we mean. What's the meaning of this? So a meaning. So we define the metric as an inner product, right? So we need to say that whenever we have two elements, psi and eta, in the holomorphic tangent space, but there the basis is given by the dzj's. So any psi looks like sum of psi j dzj, and any eta looks like sum of a k, say, of eta k dzk. So whenever we give ourselves two 1-0 vector fields, in other words, 1-0 tangent vectors at the point x, we have the meaning of the above notation is the following. The inner product between psi and eta at x with respect to g, right, is sum over j and k from 1 to n. So I'm explaining the meaning of this notation here for g. Sum of gj k bar psi j eta k. And also note that we necessarily have the coefficients here form gjk bar, form a Hermitian matrix. So what does that mean? It means that gjk bar, if we conjugate this, we get it's symmetric with respect to the diagonal. So we get gkj bar for every j and k. So this means actually that the matrix, the coefficient matrix is Hermitian. The coefficient matrix gjk bar over j and k is Hermitian. So this is the meaning of being Hermitian. It is the complex analog of being symmetric, right? In the real case, there is no conjugation here. So this property in the real case would be gjk equals gkj. In the complex case, we need to conjugate. So this is the Hermitian property. Why is it Hermitian? Because it is a consequence of the fact, let me write in this way, it's a consequence of the fact that the inner product is positive definite. So this is what an inner product is. It's necessarily positive definite. So this means that the coefficient matrix is actually positive definite. This matrix is even positive definite as a matrix in the sense that its eigenvalues are strictly positive. And positivity implies the Hermitian property. Being Hermitian is the analog for matrices of being real for numbers. And for numbers, if you're positive, you're real, right? Right, so this is the first point of view on metrics. This was the definition. But now let's say second point of view. Second point of view on Hermitian metrics. And actually, it is this second point of view that we usually adopt. So the first one is to say that Hermitian metric is an inner product on each tangent space. But the second point of view is the following. Let's start with a theorem, which is actually very simple. Theorem. There is an isomorphism. Let's write in this way. The following map is bijective. Now, what is the map here? I'm taking on the left Hermitian metric in the sense that we defined before, that is sum over j and k from 1 to n of g j k bar dzj tensor dz bar k. So this one lives in, let's call the space Herm of X, the space of Hermitian metrics, right? Hermitian metrics on X. And we map this to the following object. To the 1-1 form, let's call it omega or omega sub g, defined in the following way. It's almost the same thing as here, except that we transform the tensor product into a wedge product and put an I. So sum of g, j, k bar, we don't change the coefficients. We put an I and then gj, dzj, wedge, dz bar k. So this one is a C infinity 1-1 form on X, and it is positive definite. So take positive definite to mean by definition. Actually, there is an equivalent definition of this, but let's go fast. Let's take as the definition of this, the fact that the coefficient matrix is positive definite as a matrix. And this is independent of the choice of coordinates. So this property is independent of the choice of complex coordinates. So this is a difference with respect to the real case, because in the real case, if you change the real coordinates, you don't get positivity. Positivity is a complex notion. You don't have positivity in the real case. So it's an easy exercise to show that if you change coordinates, of course, you get a different matrix here for the coefficients. But if the coefficient matrix is positive definite in one choice of coordinates, it stays positive definite in any other choice of coordinates. So this map that takes any g, a Hermitian metric, to omega g, so omega g is a CMT 1-1 form. So going from matrix to positive definite CMT 1-1 forms is bijective. So now this is easy to show, proof. The proof is easy. Let me just describe what a metric means. So take omega g, what it means to apply to a pair of 1-0 tangent vectors xi eta. So we saw above what it means to apply g to xi eta. It means this, right? Xi eta, when you apply g to this is the inner product. So you can also denote it by g of x applied to xi eta. Right? This is what we saw for g. It just take the product psi j eta k with a coefficient. Now for omega, it's slightly different. And the theorem says that you get a bijection between the two objects. So what do we get for omega? It's going to be sum over j and k from 1 to n. The coefficients don't change. This is still gj k bar. But this thing now, when you apply to xi eta, is not just the product psi j eta k. It's a determinant. You apply dzj on the first column, you put dzj applied to each of psi and eta. So when dz applies to xi, you get xi j. When dz applies to eta, you get eta k. And now for dz bar k, when you apply dzk to xi, you get xi k, and then the conjugate, because it's dz bar k. And then when you apply dz bar k to eta, you get eta k with and conjugate, right? So this one is not just xi j eta bar k as we had before. I'm sorry, it was eta bar k here. Sorry, just correct this. Because an inner product, a complex inner product is of course sesquilinear, right? It's linear in the C linear in the first argument in psi, and C antilinear in the second argument. So it's eta bar k here, right? Whereas for metric, for the metric, it's not just xi j eta bar k. This determinant has two terms, xi j eta bar k minus xi bar k eta. What did I write here? It's eta j here. So once again, dzj, on the first column, we put dzj applied to each of xi and eta. So dzj applied to xi j, dzj applied to eta is eta j. And on the second column, we put dz bar k applied to each of these. So xi k bar, eta bar k. So you get xi j eta bar k minus xi k bar eta j. So we have this new term, which we didn't have in the case of the inner product. But then the theorem says that there's a bijection between the two. And I think the bijection is written invariantly, right? Because what I wrote here is in local coordinates, but written invariantly written is that one of them, I never remember which one is it. Which one is the minus twice the imaginary part of the other one? I think it's G, because minus twice the imaginary part of omega sub G. Well, let's say it's this way. It's, or otherwise, omega is minus twice the imaginary part of G, but I think it's this way, right? So what I wrote here in coordinates actually can be written invariant in this form. And this map is a bijection, right? So, QED. So we have 2 points of view on metrics. The most usually adopted is the form, differential form point of view, right? This one here. Metrics are C infinity, positive definite C infinity 1-1 forms on the manifolds, but they're also inner products on the tangent space, on the tangent bundle. Right. So these are Hermitian metrics. And now, immediate observation. Hermitian metrics always exist on any manifold. Hermitian metrics always exist. Always exist on X. Why? Because locally, of course, they exist. So proof. Locally, they exist. Take any positive definite matrix omega j k bar over j and k from 1 to n as coefficient matrix, and then put omega to be the sum over j and k from 1 to n of omega jk bar I dzj, which I dz bar k. So locally, they obviously exist. And now we can globalize this using a partition of unity, right? We can globalize using a partition of unity. In other words, we cover our manifold by coordinate charts. In each coordinate chart, we have a Hermitian metric. Take any Hermitian metric, omega alpha for the chart U alpha, any Hermitian metric omega beta for the chart U beta, and then use a partition of unity to glue them together, right? And then put omega to be sum of, say, theta alpha omega alpha, sum of alpha, where theta alpha is the partition of unity. Is a partition of unity. Right, so this is obvious. Hermitian metrics always exist. But now what we're going to see now aim is to study the geometry of X, the geometry of X by studying the special types of Hermitian metrics. So special, right? Of Hermitian metrics it supports. Of Hermitian metrics it supports. And now let us start with defining the most special metric, which is called Kähler metric. Definition. A Hermitian metric omega a Hermitian metric omega on X is Kähler if and only if, by definition, it is closed. If and only if d omega is 0. So it looks very simple. The definition is very simple. A Kähler metric is a Hermitian metric that is closed as a 1 on 4. So this closedness condition is actually is called the symplectic condition. Right? It is a term that also exists in real geometry, the notion of symplectic structure. But what is special to the complex context is that it is positive definite. In real geometry, you don't have positivity. Right? So Kähler metric is this. And now the thing is that these metrics need not exist. Now, of the properties. So an obvious property is the following. For every k from 1 to n, if we take omega to the power k, so this one is declosed, right? Because omega is declosed by definition, and d of omega to the power k is what? It is k omega to the power k minus 1 wedge d omega, but d omega is 0 by definition. So d omega to the power k is also 0, and therefore omega to the power k defines a de Rham cohomology class, right? Being closed, it defines a de Rham cohomology class of degree k. So it lives in hk de Rham of xc. Right, so for every k, we get this de Rham cohomology class, but the observation is that fundamentally, so crucially, this class is always non-zero. So in other words, a Kähler metric, if X is compact. So crucially, if X is compact, these de Rham cohomology classes are non-zero. Omega to the power k, de Rham of this, is non-zero for every k, from 0, 1 up to the complex dimension n of the manifold. Now, what is so in particular, the Betti number, the kth 2k Betti number, right? Why 2k? Because omega as a 1 on form is a 2 form, right? So omega to the power k is a kk form, hence a 2k form. The total degree is 2k, hence the 2k form. And actually, it's h2k here, sorry. Right, omega to the power k is a 2k form, so it lives in h2k de Rham. So in particular, if omega is a Kähler metric, the Betti numbers of even rank are non-zero. Actually, it's even better than that, but this is the first thing that we get from this. If X is compact, the Betti numbers are non-zero, and therefore, if one of the Betti numbers of even rank is zero, the manifold cannot be Kähler. And the Betti numbers, remember, depend only on the differentiable structure. So if you have a smooth manifold such that one of its Betti numbers of even rank is zero, no complex structure that admits a Kähler metric can exist on the manifold. So if there exists a K from 0, 1 up to n such that B to K is 0, then no, I have to finish here. Then there exists no complex structure on X supporting a Kähler metric. So let me say in 30 seconds the proof of this. So why is the Durham class non-zero? Because if omega to the power k were d-exact, in other words, the Durham class was 0, then omega to the power n would also be d-exact. Because it's omega to the power n is omega to the power k, which omega to the power n minus k. Omega to the power n minus k is at least d-closed because omega is d-closed. And the product between an exact form and a closed form is exact. But then the integral of omega to the power n, on the one hand, would have to be 0 because by Stokes, because omega to the power n would then be d-exact. So we apply Stokes. The manifold X is compact with no boundary, right? So if we integrate something that's d of something, you get get 0 if there is no boundary. But on the other hand, this has to be positive, strictly positive, because omega is strictly positive. So, and this implies that the determinant of the coefficient matrix is, of course, strictly positive, but this is exactly the coefficient omega to the power n, right? Omega to the power n over n factorial, if you write it in local coordinates, is exactly the determinant of the matrix, of the coefficient matrix, times I dz1, wedge dz bar 1, wedge up to I dzn, wedge dz bar n. So being strictly positive, this is a complex phenomenon. You don't have this in the real case. All the eigenvalues are strictly positive because this is what means for a form to be positive definite, and therefore the determinant, which is the product of the eigenvalues, is strictly positive. But on the other hand, so the integral would be strictly positive, but on the other hand, it would have to be 0 if omega to the power k were d-exact, because then omega to the power n would have to be d-exact by Stokes. So this, of course, is a contradiction. All right, so this is all for today. We'll see next time some examples of Kähler metrics, and crucially, examples of other special metrics, which are weaker than the Kähler ones, but have nice properties. And one of the main properties of Kähler metrics is that if a Kähler metric exists, then the manifold is a DD-bar manifold. In particular, on Kähler manifolds, you have a Hodge decomposition and a Hodge symmetry. So in particular, you can relate the two types of structures, differentiable and complex, using the corresponding cohomologies, the Durham cohomology and the Botchern cohomology, and the Dolbeau cohomology and so on. Well, thank you very much.
Welcome. Any question? One small remark about that too. So it is, can we say it homotopy invariant or topological invariant? All of the
topological invariance.
I think, yeah, maybe homotopy invariant is much refined.
The Durham ones are topological invariants. The others are just complex invariants. The invariants of the complex structure.
All right. Thank you very much.
Yeah, thank you.
Another question. All right.